Ladies and gentlemen, welcome to this session, which is called Studying Electron. Can we go back to the first slide? Which is called Filming Electron in Motion. And I'm the moderator, so I will present in the next 5 minutes the speakers of this session. And I start already with the first one, who is Jan Luning, coming from the Helmholtz-Zentrum in Berlin as the scientific director. And he's going to tell us why it's important to study new materials. And you know that materials development has been influencing our evolution, starting from, for example, the Stone Age and going to the Graphene Age, to the Graphene Age, as you can see from the figure over there. And you know that graphene right now has a lot of applications. Some of them are concerning system to collect light, so to harvest light, so solar cells. And it's very important to improve the efficiency in collecting light to fight against the global warming. Actually, you know that our planet is suffering. We are facing global issues. And the second speaker, Katarina Biscari, who is the director of the ALBA Synchrotron in Barcelona, she will point out how science can help in fight those global issues, and especially concerning the climate and the environment. There are, many sources of carbon footprint on Earth, and one is coming from data centers. Usually, data centers are belonging, the majority, to service providers like Google or Facebook and so on and so forth. And the problem is that whenever we use Google or we watch a movie on Netflix, we are using those data centers in the sense that the data are stored in data centers. And to store the data, you need a lot of water and a lot of electricity. Actually, there are many calculations, but in the end, watching a film on Netflix corresponds to produce the same quantity of CO2 than driving a car, a mid-sized car, for 20 kilometers, 30 kilometers. So, they are counting quite a lot in the global warming. And that's why Stefan Eisebit, director of the Max Born Institute in Berlin, he will talk about how to improve the data storage in a way such that we can reduce this footprint, carbon footprint on Earth. As you can see from the cartoon, you have many industries which are producing a lot of CO2 and a lot of pollution, and many of them are chemical industries. And chemical industries, basically 80% of the chemical industries, they are using catalysis. And that's why the last speaker, Majed Sergi from Lausanne, actually is professor in the École Polytechnique Fédérale de Lausanne, is going to tell us how to improve catalytic processes, because usually, as I said, chemical industries, they're using catalysis, which is a process by which one can increase the rate of chemical reactions. And usually, for example, as you can see from the figure, you have a reaction between two molecules, which can be made much more easy if you use a system, a media, which is called catalyst. And basically, the majority of the science that you will see has been obtained using large-scale facilities. When I talk about large-scale facilities, I mean facilities where you have an accelerator producing photons, so X-rays, for example, and those photons are used to do experiments. We have many facilities in Europe, and actually they are forming a consortium called LIPS. And in particular, you can see that in Trieste, there is one facility, which is from the figure, which is named Elettra Synchrotron Trieste. And in Elettra, we are running basically two large-scale facilities, a synchrotron and a free electron laser. All this concept will be clearer, much more clearer later on during the presentations. But the message to take home is that there are many advantages in using large-scale facilities. First of all, they are open to external users, so anybody from university or research lab can apply to get beam time, and basically for free, because I mean there is nothing to pay to use those facilities, and moreover, those facilities, they present unique features that you cannot find in normal small labs at the universities and so on and so forth. That's why if you sum up all the facilities in Europe, we have thousands of users per year using these infrastructures and to produce new science. And this was my introduction. So I hope you will enjoy this session, and I give the floor to the first speaker, which is actually online, so the floor stays free. But Jan Luning, we cannot hear you.
Claudio,
okay.
Thank you very much for the introduction. Thank you. Let me also at this point thank the people behind ESOF for making it possible for us to have this wonderful event taking place today. I very much appreciate that we have a chance to share our message here with the people being on site and also online. You already made the point, materials are the cornerstone, are the basis for advancing on these challenges that we face. Today, I show here as one of the many different ways how to look at this, the global challenges identified by the Horizon Europe program. And to quickly just show you is, I mean, there are many of these directly related to new materials. We need new materials to convert solar energy into other forms of energies. We need new materials to advance our batteries such that we can store the energies or find alternative ways. And as you pointed out, the digital industry, with the ever increasing amount of data that we store and have to handle, we need to find new materials to actually be able to make this more efficient. And if possible, of course, also on smaller length scales. Even in the context of natural resources, we need to find ways how we can get more around this more in a sustainable fashion and also preserve more our environment. And here materials, how we can, for example, handle our waste that is poisoning our oceans is one of the many challenges that we face in this context. Now, nothing more than health with the current COVID pandemic. We, of course, need urgently drugs and vaccinations to be able to get back to a more comfortable way and healthy, of course, also to cope with this pandemic so that we can also come back and meet in person. But there are also fields like implants, new materials are needed that have better biocompatibility so that we can actually help our aging population to cope with issues that come simply with age. Now, X-rays are actually provide us with fantastic tools to advance material science. And let me just show you one of the unique properties that actually X-ray based analytical tools offer us. There is already from Röntgen discovered, of course, the way that we can look through things that are otherwise opaque to our eyes. And we can look inside of bodies or objects and actually derive information what is inside other things. But we can also make things visible that we could not even see with our eyes because they are not sensitive to that. And this is shown here with an example of a magnetic hard disk where we see the bit pattern, a test pattern written onto these magnetic layers. And Stefan will show more examples on that, how we actually benefit from being able to see things that we could otherwise not see. Now, we can also don't see atoms with light and molecular structures. And here we have fantastic tools like diffraction and spectroscopy techniques, which we can look at crystalline ordered materials, which has, of course, given us the insight into the structure of the DNA. But equally also, we can use spectroscopy techniques to find out how molecules are composed. And for example, illustrated here, how they actually attach to a surface, which is, of course, of highest relevance in the context of catalytic processes. as Majed will show in his talk later on. We can't only see atoms, we can also see what is the electrons are doing. And this is this electronic structure that defines the functioning of materials. We can make visible where the electrons are, how they're oriented in their orbitals. And I will at the end of my talk show today an example how we can actually really visualize this concept of orbitals using X-ray techniques. But we can also get, of course, information about the direction into which electrons move and their kinetic energy, and can from that derive their electronic properties, for example, that are defining the superconducting properties of materials. Last but not least, already hinted on in my first graph, we are sensitive to magnetic properties, and we're not only sensitive to it, we can also quantify the magnetic properties of materials. And I want to illustrate here one very important point, and that is we are actually able with the X-rays to selectively probe individual components of complicated compound materials. We can see what the antiferromagnetic properties in one layer are, how the ferromagnetic properties of an adjacent layer are related to it, while a further layer further away may have a different magnetic orientation or properties. And this allows us X-ray techniques with the selectivity, with the quantitative information that we can derive from these signals to get a very detailed, fine insight into these tools. Now, you already hinted at this, that we need for these large-scale facilities, because we need these very exquisite X-ray beams. And we are today in this fortunate situation that we have two different types. We have the so-called storage ring-based synchrotron sources that actually provide us with a very brilliant beam, where we have quasi-continuous wave irradiation available. Of course, it is not continuous. It is composed out of little flashes. In the storage ring, these packages of electrons are put into the storage ring and stored for hours and days. And we get, every time one of these packages flies by one of our experimental stations, we get actually a flash. But since there are so many, it looks to an experiment as a quasi-continuous source. And with that, we get a very high stability, and with that, the sensitivity to characterize materials on very, very subtle details. They are pulsed at the end nevertheless, and so we can use the pulse structures for time experiments, and with that we get to big experiments with time resolution of tens of picoseconds, which corresponds to the collective motions of atoms or the transfer of charges in materials. Of course, we can look at slower phenomena, and I will show that later in my talk. Now, getting down to the time scale of the fundamental excitation of the fundamental processes, this we can do with the free electron laser sources, where we use individual electron packages to actually get insight into a phenomenon, into the time evolution, and can follow with very high time resolution fundamental processes in all different types of science. These sources are extremely brilliant. The electron packages are very small, they're very short, and due to that we have the quasi-point source, and with that we have a laser and get a very high degree of coherence. And again, Stefan will show us later how we can exploit this coherence to get insight into the materials. Now with these, we are in this, as you said, we have several of these sources in Europe. If you actually look at the world map, you see that we have in the Northern Hemisphere that most of these sources, with the exception of two, one in Brasilia and one in Australia. But then if you look at the clustering, you see that in Europe, we are in the fortunate situation having a variety of these sources optimized for different aspects. And with that, we give our researchers, but also to industry, unique opportunities to look into materials properties. And while these sources have been developed over the past decades, now it is our challenge to make them ready for the future. And Katarina will give you an idea how, with this league of European accelerator-based photon sources, we are driving into that direction. Now, we use these to study phenomena on different time and length scales, and we can actually cover all length and time scales that are relevant for material science. We'll show you examples where we go from macroscopic measurements to mesoscopic measurements to resolve, for example, the architecture of a CPU. We get atomic resolution via the diffraction and the electron orbitals that I mentioned before. And we do this on timescales that bridge from the fundamental excitations to the charge transfer diffusion processes typically taking place on the microsecond, and then operando studies that are on the millisecond to hour timescales. Let me start with the first example, and this is the goal to get to a hydrogen-based economy that doesn't need free hydrogen. meaning we try to find a way how to get away from handling large quantities of atomic elemental hydrogen. And the idea here is to use a liquid carrier, an organic carrier is what we're pursuing here, is where we can actually store the hydrogen by hydrogenation in organic molecules, and that way transport the hydrogen without the risk of any explosion or being inflammable to the point where we need it, or store it until we need it when the sun, or for example, has gone away in the evening. And then we regain the hydrogen from this liquid by dehydrogenation, and we can produce energy, for example, in a fuel cell. And a study that was pursued a while ago at one of our facilities is shown here. You have to see it at this left figure first. We see what the electronic structure of the nitrogen atoms looks like. And we start with a very clean surface of platinum here, and we expose the surface to the molecules in the vacuum chamber. And we see at first on the left, we see the monolayer adsorption of these molecules. And then after some time, when we have the monolayer, there starts to build a second layer, and then of course a multi-layer structure. So this is just time. We let time go by and follow the process. And then after some time, when we're sure that we have a good coverage, then we stop the deposition of the molecules by closing the valve, and we start to heat the sample. And what we see as a first is that the multi-layer disappears and we remain with the beautiful monolayer of these molecules adsorbed on the surface. But then when we increase further the temperature, we see a change in the spectra. And this, if you combine it also with the information we get from the carbon atoms, we can interpret as actually a dehydrogenation of the molecules, which leads, in this case of this particular molecule, to the desorption, a dehydrogenation of 12 hydrogen atoms from this molecule. And only when we go further up at the temperature, about 450 degrees, the molecule starts to disintegrate. So here we do a macroscopic experiment. We follow in time how it evolves. Now, let me add spatial resolution to it. And an example that I want to use for that is a battery. And one of the ideas that we're currently pursuing is that we could use silicon electrodes to actually increase the capacity of these batteries. Now, the shortcoming is that with the incorporation of the lithium in the silicon electrodes, we have a change in volume and expansion, which leads to cracks in these electrodes. And so after a few cycles, the battery becomes less efficient and we lose the advantage that we had at the beginning. So it's very important to understand when this happens and whether we could prevent this or what we could do. And so by looking inside into this material, looking through the material using X-ray radiography, we can actually see that these cracks, which are initially here at A visible, that they disappear during the charging. We have the lithiation of the layer, we have an expansion, the cracks fill with material. Now, when the battery is charged, there are no more cracks visible. And if we start to discharge the battery, up to a certain point, no cracks have shown up. Only when we discharge the battery completely, we get back the cracks. And this tells us that the silicon has the capacity to handle the tension of the volume change to a certain degree. But if we operate the battery within this frame from B to C, we can actually operate the battery without cracking the electrodes. We lose, of course, a little bit of the capacity, but it turns out at the end, we still gain. But in addition, of course, this insight provides us means how we can actually improve the battery behavior. Now we can add more spatial resolution, and Stefan will give an example of that. And we can go then further down using microscopy, and we can then go to the diffraction to actually obtain these beautiful images of the biologically relevant macromolecules. This is the protease of the SARS-CoV virus. And what you actually learn from this is not only that we see the structure, but we can do also then experiments and see how we can incorporate into this protease molecules, how they can bind to it, and with that way lay the foundation for a medication against the consequences of an infection. This is atomic structure. Now, if we do the next step, we can actually also go to the electronic structure. And we have developed in quantum mechanics the concept of the wave functions where we can actually derive where the electrons are in space. And this is illustrated here on the left side. We have here the prediction how a certain electronic orbital would look like in space. And if we do a transformation for that into the, so to speak, energy space, we get an image from this how this would look like in this different complementary space. And the important part is that this is the one that we can measure. And so we can compare our measurement, which is shown here on the left side, with a prediction from theory. And from that, in an indirect fashion, go back and see whether we have a confirmation between our calculation and our measurement. But of course, this is only one way. What we really would like to do is to go back from this way and see how the molecule looks, what it looks like. And then to go back there, we need to overcome what is called the phase problem, which is something which is generally known as a limitation when you only measure intensities of a wave, but not its phase. That means the time, so to speak, when the wave arrives. But we have developed with the progress of computers today means that using algorithms, we can actually do this backpropagation. And I'll show you here an example how we actually came back from this measurement to a graphical visualization of this orbital in real space. And if you compare, you see perfect agreement between what the experiment shows and what the theory predicts. And this is actually very satisfying for us as a scientist because it really shows us a confirmation, a visual confirmation of our concept of the electronic structure and electron orbitals. Now, all of this becomes possible due to the unique properties of X-ray techniques, and I very much hope that I could give you a teaser of that and look forward to your questions. Thank you very much.
Thank you very much, Jan, for this interesting talk. So now there is space for a couple of questions, if there is any. I didn't get any question from the web, so no questions. So I have just one for you, Jan, so maybe we can talk a little bit later at the end of the session. You said you measured the protease of the SARS-CoV-2. Did you plan, I mean, are you planning, because maybe you have still to figure out how to do it, but are you planning to do experiments also on the spike protein or to the dealing with the entire virus? Because I know that there are recent measurements on the entire virus measured by cryo-EM, and they saw some funny behavior of the spike protein. So I don't know if you are planning to do some experiment just on the spike or maybe on the entire virus.
So if I speak, of course, for the entire X-ray community, of course, I mean, protein crystallography, X-ray-based protein crystallography is the leading technique to get insight into the structures. Cryo-TEM is a very wonderful complementary technique, but if you want to have the high resolution to see in very much detail, it is still no way around the X-ray protein crystallography. Now, we here in Berlin at our facility ourselves, we actually specialized on doing fragment screening, meaning we're using these proteins and we see how small molecules can adapt to this. And so we personally don't do this, what you mentioned, but this is of course pursued at other facilities that Katarina will introduce in a second.
Okay, so any other question? We have no questions from the audience, no questions from the web. So we can go to the next speaker, Katarina Biscari. She is director of the ALBA Synchrotron in Barcelona. And as I said at the beginning, she will tell us how science can fight against global issues like dealing with the climate and the environment. So Katarina, the floor is yours.
Thank you, Claudio, for the presentation, and thanks to the organizer for this invitation. I'm here representing, of course, not only my facility, the ALBA Synchrotron, but the LEAPS consortium. And therefore, I would like to spend some time at the beginning to present what this consortium is in Europe. It's a consortium of all the photon source based on accelerators, as Jan just mentioned, the synchrotrons and the FERs, and we are talking in Europe, and we're talking of 19 facilities, plus one associate, which is Sesame in Jordan. And altogether, we are serving a community of tens of thousands of users, as mentioned also by Claudio, users who come from all over the Europe and also all over the world, and that can use more than 300 operating stations. Altogether, they offer more than 800,000 hours per year. So it's a real source of science and of capacity for technological and scientific advance. And all these facilities join together in a consortium to promote the quality and the impact of the science, and to work together to develop common projects to sum up the forces and the capacity of each of us for a better service to the society. And you can find the information in our webpage. I just want to mention some of the main points that we have been working on from the beginning. We started with collaborating, putting under the umbrella of LEAPS what was already a collaboration existing since the beginning of this field in Europe, but now is more formally recognized. And we started in 2017. We developed a strategy, analysis of our landscape, mainly meant foreseeing what should be in the future the development of the field, considering all the capacities in Europe. We are working, of course, in collaboration also with the European Commission aims and programs. We are responding to the input we get from them on the main points that want to be the future of the science in Europe. For example, we have answered with position paper on the battery challenge, on the emissions, and then, of course, as mentioned already several times, on fighting the COVID-19. And it's not only LEAPS, it's not only the infrastructure for which are providing photons produced by the electrons, but is also the collaboration and the complementarity with other research infrastructure, with other analytical research infrastructures. And we are also working in optimizing the collaboration and the complementarity with neutrons, lasers, ions, protons, high magnetic fields, and electron microscopes. And there is now is in a starting. We started in February to work together with this other consortia. We formed the overall umbrella, which is called ARIE, Analytical Research Infrastructure in Europe. And also here, the effort is meant to have a better result with the resources that are already in Europe, and especially also to provide paths for the development. When I mean area, I mean more than 150 research infrastructures. So it's really a powerful tool that Europe has, and that must be valued for not only by those who are working in the infrastructure, by the user, but also by the funding agencies. And of course, the most urgent challenge is fighting against the COVID. It's not only finding the vaccine, the cure, but also learning to live with the virus and learning to tackle these problems also in the future if something similar happens. And therefore there are it's not only LEAPS that has been working on showing what can be done with the LEAPS facility, but also all the other infrastructures. And some of these pictures you have already seen in the presentation by Jan, but I want to show that the European research infrastructure community has answered quickly to the COVID-19 threat, and there were opening quick access modes for in all the facilities. There were, and of course, are going on research in all of them, projects not only for coming from the users, but organized even by the same facilities themselves. And here is just a few examples of the many that are going on in Europe, and of course, in complete collaboration with what is happening around the world. So let's go now to the subject of my talk, which in principle is climate and environment. And I want to show some example of what the facilities providing photons from electrons are able to contribute to solve the problems corresponding to climate. Of course, we have cutting-edge techniques for example, helping in the generation of climate-neutral energy generation. You have seen some example of, for example, on batteries, but it's not only that. We need the availability and the knowledge and the development of the right materials, and the facilities based on photons are essential for the development of photovoltaics, for example, the perovskite and the biomass generation, green hydrogen, and how to capture and reuse carbon. Another field very important is the energy storage, of course, and the conversion for clean transport and mobility. And here again comes the development of batteries, supercapacitors, fuel cells. The capacity of our facilities for studying problems in a multi-scale range, from the atom range to the whole device, is really a powerful tool, because it can help in understanding the bulk properties and the interface of the components which determine the performance of batteries, as was shown also by Jan. Another important development, which is newer but is growing very much, is the development of devices quantum enabled, which are using less power, less energy, and this is very important for the future in order not to increase the need of production of energy of the world. And of course, we have the Internet of Things, whose demand of energy is continuously increasing. It is foreseen that for 2030, the IoT will demand more than 20% of the global energy production, and today is half of that, the percentage. So we need really energy efficient approaches and materials, nanostructured materials for information generation, processing, and storage. Another point is, for example, the production of improving with biofuel, understanding how they crystallize, because this can cause engine failure, or investigating the potential use of glycerin. And I want to show some examples which are results of experiments done in some of our facilities. This is an experiment which was where one of the beamlines of ALMA was used for NEXAS, and it is related to fighting the concentration of CO2 in the atmosphere, which is dramatically growing, even during the lockdown, has not diminished so much as expected. And this is one of the most urgent problems for the future of the humanity. And here we have an example of ruthenium carbon catalyst. I won't go into the details also because catalysis will be one of the subject of the next talk. But it's important to mention this for the climate, for the fighting the climate change. And here we have another example. This one made at one of the Petra beamline in Hamburg for looking, understanding really how the corners and edges can increase the effectiveness of catalysis with an experiment which was really a window on what is the inner dynamics of the catalytic materials. And always in Hamburg, this time in the FEL, in Flash, we have another example in which by superposition of three synchronized lasers, two external lasers plus the laser itself produced by the accelerator, the flash pulse, which is a free electron laser, they were able to investigate the dynamic of the halogen substitute benzene, which is one of the components of fuel. And then we go into the part corresponding to environment and food. Here, of course, let me see if this works. Here we have an example of what, no, it doesn't work. I wanted to show you here at the edge an example at ESRF where there is the tomography of a cube, this cube that you use in the kitchen to give flavor to the cooking, and they were able to show how all the components are distributed in the cube for improving the production of food. But going to the food, it's one of the fields very important is understanding, for example, the plant growth, how the plants respond to growth hormone, or which is the effect of fertilizer and pesticide. And this is very important, not only to develop and to optimize the production of food in the part of the world where we have a good production and a very good alimentation, but it's more important still to understand this, to improve the production of food in those parts of the world which are under which do not have the right nutrition. So improving there the plant understanding is crucial for the future of the humanity. And also understanding what is the pollution effect in food and the response to pollutants and to pesticides. And of course, another big field of research is what is related to the food industry, not only the food, but also the packaging. And all this research, there is a strong correlation with industry, because of course, also here, and what I was also mentioning before, the collaboration with industry is essential, and all our facilities are providing access also to industry, even with dedicated European Commission programs. Another very important part is the environment, knowing the environment, for example, monitoring what are the waste products from industry or from human activities, understanding our climate history, which is also very important to foresee what will be the climate evolution in the future. Understanding and finding a solution for water pollution, this is essential for the health. And for example, developing this metal organic framework for removing pollutants. Developing biodegradable packaging, and another important essential part for the environment is our relationship with plastic, both all the industry which is using plastic for helping the most of our activities, but then there is the problem of recycling and monitoring also the plastic pollution. Also here I will show a few a minor component of the thousands of examples that are around not only Europe but all around the world. But just to show, for example, the discovering of the principle of plant response to the auxin hormone, which is the hormone of growth. And this is very important for the design of new crops resistant to certain diseases or to drought or flood. And another important thing is also understanding the dynamics of water inside the plants, and mainly in the seedling stage, in which this is the most susceptible during the tree life. And this example shown here has been done in Elettra, that's where you are now, those of you who have the luck of being present in this conference, using Synchrotron Radiation to visualize in a non-destructive way the plant conduits. And very important also is to understand which is the health of what we are having in our plates, in our dishes when we eat. And for example, there is a study done here at Alba together with researchers also from France on the zinc storing mechanism in oysters and mussels in the Mediterranean and in the Atlantic, which shows not only the content but also shows the capacity of these mussels to be indicators of metal pollution. So even they can be used as diagnostic of what is the metal pollution in our seas. And another important element which is important in our alimentation is the selenium. And there are some parts in the world where the earth where the plants are growing is not rich of selenium. So it's very important to understand how to enrich the final product in order to have a better alimentation from the crops. This is something which is also a study which is also being done here at Alba together with other institutions. And finally, as the last example, I want to show how we can help in fighting the plastic waste and how we can help in better recycling for PET materials. Here I have two examples. One is recently found enzyme, an engineering enzyme which efficiently recycles PET, and another one which was done in Berlin is the discovery of a bacterium, what they call molecular scissors, that grows on PET and can help in digest these plastic polymers, and they can break them down and so help also in the recycling. And finally, always talking of plastic, everybody knows that there is plastic pollution in the sea, in the waters, And this is a field which is much in development. I am showing on the left a graph. You won't see the numbers, but it's in the abscissas of the last 10 years, let's say, and the number of papers dedicated to microplastic pollution in green and nano-plastic pollution in black. So we can see that this a growing interest on understanding, measuring, and then find solutions for this pollution. And there are analytical tools which are used today, mainly the transmission electron microscope to determine the morphology, and also the transform infrared to differentiate polymers, but for particles above 3 microns. And this is also done in synchrotrons. And on the left, you can see recently, it was published just a few days ago, a paper on a study done using also the infrared beam line in ALBA, where they found microplastics in 9 lakes in Patagonia, in a place where the human activity is not so high, but even there they found that there are the water is polluted by microplastic. But the idea is to develop in the synchrotrons the SANES, because the SANES of C1 is very sensitive, and therefore it would be a perfect way to focus on the polymer characterization and to develop tools able to detect nanoplastic in the water. So this is something which is a field in development. I wanted to finish with this because, of course, there are many things that are being done, but what I want to mention with this last slide is that our field is a field in continuous development, in continuous searching for new techniques, new instruments that are able to better understand or to fight new challenges that our society is facing. And with this, I thank all of you for your attention.
So thank you very much, Katerina. I don't know if there is any question. There is space for 1 or 2 questions from the audience. No questions. I check on the web. There are no questions. Everything was extremely clear. And I have just a general question. We saw many experiments which are basically at the cutting edge. Then you have some delay time between this experiment and the application, if any application comes. Do you have any idea how to improve this process? Because I think the time lag is pretty long, and if you have any idea how to improve this in terms of...
The time lag is long. We had, for example, we did a study of socioeconomic impact of there is a program to develop a model for studying the socioeconomic impact of research infrastructures. And in this study, we used data of ALBA to see when the patents comes after the paper is published on after the experiment is published. And there is a lag of years, of course, if it happens. And I think the best way to decrease this lag is to increase the collaboration with the industry. Increase the collaboration with the industry at the level of basic research also. I think this is very important because, of course, from the moment in which an experiment is done, and then depending on the field, up to the moment in which the application is really on the market, you need the involvement not only of the scientists, of the ideas, of the public research, but you need the involvement of industry. And therefore, it would be good to increase whatever are the projects and the effort done also by the funding agency, the public funding agency, to increase the collaboration, the interaction between the public and the private research. And there are already some ongoing projects, like the one going on in the Calypso Plus Horizon 2020 project, where there is, for the small and medium companies, there is the possibility of accessing freely the research infrastructure which are in this Calypso Plus project. And this is something that was done as a test. It has been very successful, and I think it should be a model to follow in the future, to develop and to put funding also there. I think this is the only way. And of course, when I say UC, I say also adding the possibility of interchanging staff, scientific staff, engineers between the public and the private world. Sometimes there are some kind of barriers that are maybe mental barriers, but we should eliminate these barriers, and we should do whatever is possible to increase this evolution. I also want to mention that there is a part of the research which is fundamental research, basic research, even in our infrastructure, which are, as we are showing, very much dedicated to applied science. But there is a part of fundamental and basic research which must be also very much held by the funding agencies, because without that, the ideas on how to evolve are missing or are less. So it's important also to know that a part of science is just to understand, to know, to test, to try, and also to not to be successful in sometimes. And this is very important that the funding agencies understand also this part.
Thanks a lot. And we can move to the next talk, given by Professor Stefan Eisebit. And okay. And Stefan, I mean, the floor is yours. And as I said before, he's going to tell us how to improve data storage. Because, I mean, one source of carbon footprint for sure comes from data centers, as I said before.
Okay, thank you very much, Claudio. Welcome, everybody. As you just said, I will be talking about data storage, and I will be talking about magnetic data storage in particular, and I'll come to the point, why do we actually have to film electrons in motion? Title of our session here. So if you look at magnetic data storage, this all started with tape drives and things like that. And what you see in this photograph here is the first commercial hard drive where you have a spinning disk. This is the RAMAC, built in 1956. And ever since, of course, the technology in how we store data magnetically has improved tremendously, as you all know. And today, of course, we can buy handheld devices like your cell phones, which easily store hundreds of gigabytes of data. And to put this into more familiar units, the old RAMAC could store one song, one piece of music, basically 5 megabytes was the total capacity. Whereas today it's easy to buy, to store tens of thousands of songs in one device. Now you may say, in my cell phone, there is no hard drive, there's no spinning disk there, it's all solid state memory. But this is still a very important technology. And in particular, when you think about all the data that's in the cloud, which really, of course, is on physical storage media, this is all on spinning hard disk drives. And the reason for that is that this is the cheapest way per bit of information to store information. And although it's in the cloud, it does, of course, come with a price. It's obviously not for free. And one of the things it costs a tremendous amount of electricity. So to put this into perspective here, I've written down a few numbers from a science article, a Nature article, sorry. And so the global electricity demand is about 20,000 terawatt hours. 10% of this today goes into the use of information and communication technology. So that's counting everything from using your cell phones to communication storage. And of that 10%, again, goes into data centers. So this is those cloud data centers I've been mentioning, where the data is stored and also processed. And of course, if you look at the right-hand side, the amount of energy required for this is, of course, predicted to tremendously increase. If you think about our usage of information technology, if you think about the Internet of Things to be coming, what Katarina Biscari just mentioned, this is all, of course, expected to rise. And so what you see in the right-hand side plot is an extrapolation where the green area are the data centers. And associated with that power consumption is, of course, a sizable carbon footprint. And so improving these storage devices at the end of the day is, of course, something that makes things more efficient, but also will help, hopefully, to remove reduce the carbon footprint. Now, there are very many ways you can attack such a problem. And one obvious way, and this is what has been happening strongly in the last years, is civil engineering. So to improve the way you cool these data centers. This is not in the focus of my talk, but there are other levers you have, and one more is showing here on the bottom left. If you think about the storage technology, then this is very complicated materials which are layers of thin magnetic films designed to produce a particular functionality with structures, grain structures here in the few nanometer size. So really to improve the existing technology, you need nanometer scale material science. And I think Jan and Katarina have done a good job in telling us why large-scale facilities, synchrotron radiation sources and lasers are really excellent in improving these kinds of systems, because we can see the different atoms in there. We have access to the right spatial scale and have element sensitivity. Now, beyond improving the existing technology, of course, another approach is to come up with entirely new concepts to do that. And so that is exploration that is going on, and there are various concepts which are being explored. And I'm showing you one concept there in the video, which is just running on the right-hand side. So what you're seeing there is an image of a special microscope, a Kerr microscope, which makes magnetization visible. Black and white means the material is magnetized in different directions. And so this is how data is stored on a magnetic storage medium. But now we use a laser to store that information, right? This word thanks was written by running a laser point over this material. So this is a new approach in contrast to what's been done today, where you use a magnetic field to write the zeros and the ones on a hard drive. There are, of course, other approaches too. For example, to not use a spinning disk at all anymore, but to use something that's more like a shift register, these little pillars here you see here, where the red and blue areas, again, represent areas which are magnetized one way or the other way to store information. And these are two examples which I will come in more detail to in a second. So the first example is, how can laser pulses be used to manipulate magnetization? And if we think about this, and I'll go into some detail in a minute, it really boils down to looking at what the electrons do in a material. Because at the end of the day, it's the electrons that make up the magnetization of a material. It's the motion of the electron around the nucleus and the spin of the electron that produces the magnetization. So if we really fundamentally want to understand these processes in order to improve them, we have to look at the electrons, and in particular, we have to film them doing their job, because it turns out that in many, many processes, it is the dynamics of the process that is actually determining the function. And we'll see that in a minute for this particular question here. Now, on the right-hand side, I'm showing you something that is on a slightly larger length scale. On the left-hand side, we were at the length scale of the separation of two atoms. On the right-hand side, what I'm showing you here is a particular magnetic structure. Each little arrow here represents the direction of the magnetization. So we're looking at more like a dozen atoms or so across, or even more. And this particular structure that resembles a hedgehog structure, there is a so-called magnetic Scurmion, a particular topological structure, which turns out to be particularly stable and small. And so this is one candidate that could be used to encode the bits in the storage device. And again, it's the dynamics of how these things are formed that's very important to make progress in this area. Now, let me briefly comment about the timescales involved here, because there's a probably pretty mixed audience. So this is a logarithmic timescale. Every tick, I start with a second in the middle here, and every tick to the right makes the timescale 1,000 times longer. And we're kind of used to long timescales because they encompass things like a day or a human life. So this is a always going factor of 1,000 to the right. And you see here the dinosaur extinctions, that's 10 to the power of 15 ago, and another 1,000 times longer is about the age of the Earth. So these are very, very long times. Now, if we go to the short times and we split the second into in a fraction of 1,000, then we're at a single mosquito wing beat. A few further splits further down the line is the fastest electronics we can produce technologically today. It's gigahertz electronics. But what we're interested in are processes that are even faster than that. It's the motion of atoms in a crystal, for example. This is picoseconds, 10 to the minus 12 seconds. Or it's the motions of electrons in an atom that is important to us to understand the fundamentals of how these things work. Okay, and this is why we have to film these electrons in motion. And this is possible using synchrotron sources and free electron lasers, because they generate these ultra short flashes of X-rays, which gives us a tool, a handle, how to look at these very, very fast processes. Okay, now I will go through these two examples I've outlined before. So what you see here on the left-hand side is again an image of the magnetization of a sample. Black and white means magnetized out of the screen or into the screen. And so there's a boundary here between two regions which are magnetized oppositely, and then we hit this with a single laser pulse here in the middle. And as you see, the single, very ultra-short laser pulse allows us to deterministically switch around the magnetization from white to black, from black to white. And it turns out that this process is now well understood, and it only happens in very particular material systems where we have this ferrimagnetic coupling between two different sublattices. Here, in this case, this is a gadolinium-iron alloy, and the gadolinium and the iron are coupled antiferromagnetically. And if you hit this with a laser pulse, then it turns out that these two types of atoms, the gadolinium atoms and the iron atoms, they respond with a slightly different dynamics. The iron atoms are faster than the gadolinium atoms. And that's shown on the right-hand side here. This is the magnetization in red of the gadolinium atoms as a function of time after the laser pulse hit. And this is the iron atoms. And you can see that while they're initially magnetized oppositely, for a very short time here, during this time up to 2 picoseconds or so, they're actually magnetized in the same direction. And this is really what leads to this particular functionality that you can, with a single light pulse, can switch the magnetization around. And so this makes this a potential candidate for data storage, because with a single very fast laser pulse, you can write. Now, what I want to illustrate with this slide here is that it's really the use of synchrotron radiation that helped us understand this in great detail. And this was already brought up by Jan, because we have access to inner core levels. We can really look at the different constituents of this problem separately. We can look at what is the iron doing and what is the gadolinium doing. And further, we can really probe the magnetics in a lot of detail using X-ray magnetic circular dichroism, a particular technique that allows us to monitor the orbital momentum contributing to the magnetization. So that is the magnetization that's due to the path of the electron around the nucleus, and the spin momentum where the electron spins around itself. And I don't want to go into the details of these of this work here, but the point is that this allows us really to disentangle the problem and to understand what's going on. And of course, in the next step, to use that knowledge to improve such a process and to possibly bring it to an application. My second example concerns these magnetic Skermions, these larger structures. On the left-hand side here, you see an artistic rendition of this. You see an area that is magnetized in one direction, indicated by these red arrows. And then you have this object here, this hedgehog, inverted hedgehog in this case, like structure, which could be used to encode a bit in a storage medium. And this has been actually been theoretically proposed quite a while ago. Up here, you see a simulation where you have little blobs, which are these hedgehog-like structures here, which are written. So this would correspond to bit equal 1, and the absence of such a block would be a 0. And the fun thing about these structures is that because of their particular topology, they can be very small, yet stable, which is important. If you want to store information, you want to have a lot of bits on a certain area, and you want it to stay there, you want it to be stable. And they can be moved around by current pulses. And so that makes it attractive for a storage concept where you don't have any spinning disks, but a hard, a solid state type device. And so X-rays are here very instrumental again. In this particular case, I'm showing you the example of X-ray imaging, where we can look at these structures and see them, and of course use that to study how we can optimize this. This little video here shows how we use, so this is a holographic image of these magnetic structures. These black dots are these Skermions. And what you see is that we apply a sequence of current pulses to move these little guys along such a line here. So that's what you would have to do in a prototypical storage medium. We've also shown that you can generate single Skermions, that you can write them and move them. And on the right-hand side, what you see here is that you can make these things very tiny in the right type of materials. And in ferrimagnetic materials, these can be as small as 20 nanometers or so. And this is actually the dimension you need to be competitive in the data storage industry. Furthermore, you can move them around at pretty high speeds, at 1 kilometer per second. And again, this is a performance parameter you need to build a competitive storage device. Now, this is creating and moving these things with current pulses. What we're also interested in is whether we can do this with light pulses, because I told you light pulses are very fast, and we could probably very efficiently generate these Skermions. And again, there's a lot of basic physics questions that need to be answered here. In particular, how can you actually create such a structure, which is I told you it's a stable structure. It doesn't want to be destroyed. So that, of course, creates the issue, how can you produce this structure or annihilate this structure if it's so stable? Again, X-rays and imaging with X-rays is very instrumental here. So what you see here is that starting from a magnetically uniform state, hitting this with a laser pulse, this particular material, you can generate these little Skermions if there is a small magnetic field present. So if you're in the right point of a magnetic hysteresis loop, light pulses allow you to come into a region here that you cannot get to by just cycling the magnetic field. You can produce this Skermion phase here. And the question is, how is that possible? How does that work? And here I want to show one example from work from free electron lasers. This is actually an experiment carried out at the European XFEL in Hamburg. And so here we looked at this transition state after hitting such a material with a laser pulse, with an infrared laser pulse. We then use the X-ray laser pulse at a very short time delay after that to understand what is actually going on. And so from this data, together with theoretical description, which is shown on the right-hand side, where I'll start a little movie here, what we see is, if you look at the top right, top bottom thing here, we see that we heat this up very fast with the laser pulse, and then we get into a phase where there's a lot of fluctuation of these little Skermion structures. Different Skermion structures with positive and negative charge appear, and it's in this fluctuation state where it's easy to find a pathway towards the final state where you have formed these stable Skermions. So this is some basic work which helps us understand how these Skermions are being nucleated and how they grow afterwards. And this is, I should point this out, this is also on a very fast time scale. This work shows that it's possible to generate these things within 300 picoseconds. So again, the dynamics on this fast time scale is what we can access uniquely with these types of experiments. So this is already the last slide of my presentation. What I try to show you is that there are a lot of interesting basic science questions which relate to applications, which of course, again, in turn are relevant challenges for our society in terms of looking, how do we store the data, how do we reduce the carbon footprint, and so on. And it's really the mix of techniques. It's very unique opportunities we have with synchrotron radiation, both from storage rings and from free electron lasers. And this in concert with many other techniques, time resolving or not, in our laboratories, gives us really very unique opportunities to attack these questions. And with that, I thank you for your attention.
So I have the usual question. Is there any question? Yes, one. Yeah, I think you can use the microphone.
Am I audible through the mask? Okay. Thank you very, very much. A question just on the last part of the last presentation about the Skermions. There was a discussion of requiring a phase space where there was a brief moment of very high heat in the area in which the Skermions were to be produced. I'm concerned about whether that heat production is going to be a technical limit on the usability of this kind of material for storage devices. Thank you.
Yeah, thank you for the question. That is, of course, what I've been reporting is very fundamental research, right? And we're trying to understand the pathways of how you can best form these Skermions. Now, you probably know that there's a hard drive technology that's waiting to come into the market. That's heat-assisted magnetic recording, where also a little laser is integrated into the write head of the hard drive. The actual bit is still written by a magnetic field, but the laser spot locally heats up the magnetic material so that it can be switched with a reasonably small magnetic field. And indeed, in this, so again, it's a technology that requires, again, a laser heating up the material. So this is the parallel to what you've been asking and what I've been showing. And you're fully correct. In this technology, one of the biggest issues is how to deal with the heat which is brought into the medium. Of course, you bring it in only at a very, very small point where you actually want to write. but still getting away this heat fast enough so that the bit is stable and does what it's supposed to do is a big issue. And this will also be an issue in this other approach. But I guess one can build on some of the experience and solutions that was developed in the context of this heat-assisted or thermally assisted magnetic recording.
Okay, sorry, Stefan, but we have to move to the next talk. Otherwise, we have not time enough to listen to Majed. So thanks a lot, Stefan. So we move to the last talk. Actually, the speaker is here, so physically present. So I give the floor to Majed. And, okay, this is the laser ponder. And he is going to talk about catalysis, as I said at the beginning, and this is very important concerning chemical industries.
It's not a problem. I'm not scared. Okay, thanks very much to Claudio and to the organizers for the invitation. I really appreciate being in Trieste. That's why I did come physically to Trieste to have also to meet friends and attend this meeting. So I'm going to tell you something about catalysis and why it's important to watch electrons during the catalytic processes. So first, the definition of catalysis by the International Union of Pure and Applied Chemistry is, catalysis is the process of increasing the rate of a chemical reaction by adding a substance known as a catalyst, which is not consumed in the reaction. So it's quite fantastic. You accelerate the reaction, but you don't consume the material that accelerates it. And you have different types of catalysis. Homogeneous catalysis is when you have two identical media, for example, two liquids. Heterogeneous catalysis is when you have, for example, a surface and a gas, or a surface and a liquid. Then you can have photocatalysis when it's photo-driven, and I'll give you some examples, electrocatalysis and also thermocatalysis. Now, catalysis enters in many, many processes, like what Claudio said. In life, in the energy sector, catalytic cracking, where you break long chains of hydrocarbonated molecules, fuel cells, catalytic converters for heating, photocatalysis, where you generate hydrogen under solar irradiation. I'll come back to this. In the environment, the car exhausts use rhodium or platinum to convert toxic gases into non-toxic ones. Unfortunately, catalytic processes enter also in the ozone depletion. In the chemical industry, there are many applications like methanol production, hydrogenation, and also the production of polymers, polyesters, isocyanates, all sorts of materials that are made. In fine chemistry, it comes into drug design because you want to, in biological molecules always exist in two enantiomers, left and right-handed, but biological activity uses only one of them. So it's vital for the pharmaceutical industry to be able to synthesize only one type of enantiomer. In the food industry, for example, margarine is produced by hydrogenation of fats using a nickel catalyst. I hope it's not too bad for us. Anyway, I don't consume margarine. And then it enters in many natural or man-made biological and medical processes. I'll come back to this too. Okay, now why is it so important? 90% of commercially produced chemicals in the world are made via catalytic processes, and that represents about $1 trillion in terms of value. And therefore, the demand for catalysts is extremely acute, and it amounts to about $30 billion per year. So you see, it's a crucial issue. Now, what does a catalyst do at the atomic level? So if you have a chemical reaction that takes you from A and B reactants to some product, usually you have to go over a barrier along the reaction coordinate, and that is called the transition state. So what the catalyst does is that it lowers this barrier, and it allows you to have an activation energy which is much lower than the one in the absence of a catalyst. A textbook example for that is the decomposition of hydrogen peroxide, where you have two hydrogen peroxide molecules that decompose into 2 water molecules and an oxygen. Usually, you know, this, if you can buy oxygenated water in the pharmacy, it stays stable. So there is no reaction or a very slow rate. But if now you add, for example, manganese oxide or a molecular catalyst like copper complexes, or there are other materials, chelated copper complexes, or even biological materials like catalase, which is an enzyme we have in our body, you will see that this reaction can be strongly accelerated. In particular with catalase, catalase is the most active enzyme we have in our body. It turns about 1 million hydrogen peroxides into water and oxygen per second. Yeah? And actually, you know, when you have a level of catalase that goes down, that's how you get gray hair, a problem that Claudio doesn't have. So anyway, I'll come back to catalase. The other point about, and actually related to catalase, is that many of the most important catalysts, sorry, the pointer is, seems to be, okay. Many of the most important catalysts are transition metals, and in particular metals like platinum or rhodium, which are very expensive and rare. And therefore, there is a huge effort aimed at trying to get the first row transition metals into modern catalysts, because these are abundant and cheap. Why transition metals is because they have a lot of electrons, especially in d orbitals, which they can easily donate or take. You know, they have a high chemical flexibility, which is actually the basis of coordination chemistry. And you will find them in all these molecular, biological, or solid-state catalysts. They are widespread. Okay, what are the time scales? Well, like in any physical process, length scales and distance, time scales and distance scales go hand in hand. So you have the elementary steps, and then you have catalytic cycles over nanometers and picoseconds to, let's say, microseconds, then molecular transport and so on. It can go up to days and hours and even longer. But in fact, what the basis is really the very first events are taking place during the femtosecond, picosecond time domain, and over picometers to a nanometer. As an example of a heterogeneous photocatalysis, I took a generic example where you have, say, a platinum surface with some molecules on top, and you excite the system. What you can do is either heat the surface, or you can have an electron extracted from the surface that is going to attack this molecule and break the bond. The bond breaking takes tens of femtoseconds. By the way, the electron transfer would be in the attosecond time domain. Then you have migration of the atoms that could take picoseconds. It meets another partner, it reacts with it. So again, bond formation. And then at some point, this molecule might desorb, and then that takes about tens of picoseconds. So you really need to go into these very short time scales. But the second point, which is very important, because you have techniques that go into these time scales, but don't give you element specificity, because very crucial is to know what each atom is doing. So there are not many techniques that combine time resolution and atomic specificity, except X-ray techniques. You can have atomic specificity. For example, there are STM studies or AFM studies, which are very nice, but these are not time resolved. So you have to go into ultrafast X-ray spectroscopy, because this is really element specific. And that's where the big machines, which were mentioned before, come into play. And in Europe, we have 4 such machines: the European XFEL and Swiss FEL in the hard X-ray regime, and Flash and Fermi in the soft X-ray regime. I like Fermi very much, because for me, this is the only real free electron laser. I insist. And what is the difference? What is the point about free electron laser is that compared to synchrotrons, which are fantastic machines actually, I'll show you results both from synchrotrons and free electron lasers. You see electrons give you typically 50 to 100 picosecond pulse duration with, that much, about 10 to the power 6 photons per pulse. If you go to free electron lasers, then you have a huge increase in the flux, typically 6 orders of magnitude, and you go to about 100 femtosecond or less pulse duration. So they're really very exquisite machines. Now let me show you some examples. I'll show you 3 examples. One about a solid-state catalyst, one about molecular catalyst, and the third about biological catalyst. So in this case, this is a beautiful experiment that, by the group of Nielsen to show how you can turn CO into CO2 on ruthenium-111. So they had a surface, they excited the surface, they heated in this case, and you have already the surface prepared with CO and a honeycomb structure of atomic oxygen. And so the heating starts the motion of these atoms, and at some point CO and O react, and then you get CO2, which will end up dissolving. And that they could observe very specifically by looking at the oxygen. And in the oxygen, they can distinguish between the oxygen that belongs to the CO, the oxygen that is on the surface, the atomic oxygen, and then the oxygen that belongs to the CO2. And so you could really follow the desorption from the surface in real time with atomic specificity. This is really a beautiful example. But in this case, the surface is perfect, is well prepared. In reality, and when you're doing photocatalysis or catalysis, you're using, the material, it's not super pure, and you have to go into rough surfaces. So I give you another example where solar photocatalysis is now very much being studied to produce hydrogen. And the story dates back to the early 1970s when people took titanium dioxide, which is a very cheap and abundant material, irradiated it with UV light, and so when you irradiate the material, you create holes in the valence band and electrons in the conduction band, and these electrons will migrate to the surface, at least according to them, and react with whatever you have at the surface, and they could generate hydrogen this way from water. Now, this surface is very defect-rich. And we know that in catalysis, it's actually the defects that do the job. It's not a perfect surface. So you have to go into rough landscapes. And so we took the same system and we looked with X-ray spectroscopy specifically at the titanium atom to identify these sites. And we found that these sites are typically penta-coordinated titanium centers. Usually titanium is hexa-coordinated in this system. And so if you now, we also pushed into looking at how fast, because you want to know how fast does the electron get to the defect, and what happens. So you reduce the titanium atom, and so the migration and reduction of the titanium atom is in less than 300 femtosecond. That was done at the synchrotron using the slicing. And then sometime later, people used free electron lasers and found some very nice detail. In fact, the electron trapping takes place in less than 100 femtosecond. They looked at the signals of titanium, one that gives you the electronic response, so the reduction, and the other that gives you the response of the cage structure. And you see that the cage structure responds 3 times slower after you have reduced the atom. So this is a very nice example of what you can see in these catalytic systems. Now, in terms of molecular photocatalysts, there is a whole family of transition metal complexes where you have an antenna molecule, a photoactive center, a bridge that is used as an electron relay, and a photocatalytic center, which will turn, 2 protons into hydrogen. And so the study of how all this process takes place is very important, because then you can think about designing specific photocatalysts, molecular photocatalysts. And in a very nice study by Sophie Canton and co-workers, combining femtosecond X-ray emission, X-ray diffraction, and also optical studies, they could study an analog of this kind of architecture with a ruthenium complex, a bridge, and a cobalt complex. I show this because this type of information where they could follow, the electron transfer and then the reduction of the cobalt center and even the cage relaxation, so the structural dynamics of the cobalt center, around the cobalt center, this is only possible with X-rays because these centers and that happens very often, are optically silent. So there's no way you can see the reception of the electron in this center. So you have to use X-rays, and this is really one of the cool things about X-rays. Okay, more recently, there was a very beautiful study looking at biocatalyst, the typical photosystem 2, where, as you know, the photosynthetic system turns water into oxygen, and the oxygen evolving center is a complex of, where this happens, is a complex of calcium and 4 manganese atoms which are linked by oxygen bridges. And there are 4 of these, and you have to absorb 4 photons to go through the entire cycle of producing these 4 electrons, and then breaking water to recover the 4 electrons. And therefore, this happens in this center. And for many, many years, the structure of this center was not known. And in the past 2 years, there's been some very exquisite study by the Stanford and Berkeley group where they used X-ray diffraction and X-ray emission. I'm not going to go through the details, but they could detect the 4 states through which the system goes in the so-called Koch cycle. Sorry, I forgot to say. This is a Koch cycle of the photosynthetic system. So this has been nailed down, and it's really a breakthrough achievement. Now, back to catalase, the protein that causes whitish hair. It's very similar, it's remarkably similar to hemoglobin with which we breathe. Yet, this is an enzyme and a catalyzer, but hemoglobin isn't. So it consists of 4 units, which are like myoglobin, just like hemoglobin. So you have 4 of these units. And the active center of this protein is itself a porphyrin with an iron atom. In the case of hemoglobin, it fixes oxygen and other things that you don't want to fix sometimes, like CO and NO. And in catalase, it fixes hydrogen peroxide, which then it breaks. So we wanted to understand the commonality of this active center between myoglobin, hemoglobin, catalase. So we did recently X-ray emission and X-ray absorption studies. And I'm showing the energy level diagram of this active center, the heme porphyrin. And basically combining these studies, and we did this on myoglobin with NO, and also, by the way, on another catalyst in our body, cytochrome C, which relays electrons in mitochondria. And cut long story short, what we found is that when you excite this center, you have a cascade of energy relaxation, which takes place in hundreds to tens of picoseconds. But the important thing is you go via spin state. So just a summary of this point is that breathing is all governed by spin states. And spin states, or like Stefan just told us, are states where you have spins of different orientation in the system. And these spin states, and in particular the high spin states, are long-lived. So they're available for chemical reactions like binding or releasing a ligand or taking up an electron and so on. So with this, I just want to conclude making one point important. So we are really at the dawn of such studies. There aren't that many, and they're really spectacular, and I think they're very important. The second thing I want to make is that innovation comes from fundamental research. This is very important. If we mingle too much with just applied research, then there will be no innovation. Take any application these days, it comes from fundamental research. So funding is needed. That's it.
So there is space for, I guess, one question? No, there is no space for question because we are a little bit out of time. So let's thank the speakers and also the organizer again.